Hello, this is my Physics 2 Lab 5 presentation. My introduction, I have a preview of the results, which is that the bar magnet falls more slowly through a tube of aluminum foil than it does in the air in both experimental results and computational results. The purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction computationally, and compare our computational predictions with our observed data. And we used the Teslameter app to find properties of the magnet. Fundamental principles we used in this lab were Newton's second law, Faraday's law, off-axis magnetic field, and Ohm's law. Here's our experimental setup, which you can see to the right. You can see that we dropped the bar magnet through the tube of aluminum foil and tested the time with our phones. The prediction for this lab was that the bar magnet will fall slower through the tube than the speed resulting from gravity. The system is the bar magnet and the foil tube. The surroundings is Earth and everything else. Here are our main results. Here's the data from that lab, where we timed it 5 times and found that the average was 1.522 seconds of the time that the bar magnet was in the tube. Here's the code. I highlighted the parts that we changed based off of our own experimental data. The length, width, and radius of the tube is shown there. And the mass and magnetic dipole moment, as measured from lab 3, are below. Here's a second block of code. I just highlighted the parts where I changed a specific function or I defined a specifically important part of the code. Here's the output of the code. So we were modeling the bar magnet falling through the tube of aluminum foil. And you can see the time in tube was 1.64 seconds, which is slightly different from what we measured in the lab. As far as the shape of the velocity versus time graph, you can see how the bar falls very quickly at first, then drops sharply due to the sudden resistance of the foil, then levels out into a balance between gravity and the resistive force of the foil until it eventually is at the end of the tube. Here are some observations. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing opposite directions. Which currents do they represent? According to Lenz's law, red should be counterclockwise and blue clockwise, because Lenz's law says that the forces going down should balance out the change in magnetic flux. What happens to the dynamics of the system when you flip the magnet around? They're the same, but all the forces are flipped. How does the total time in tube of your real-world system compare to that of your computational system? The bar that is in the tube for slightly longer than in the real world in the experiment, in the computational. This might be to do with not having individual weight measurements for the bar that we used. We just used a general measurement for the bar magnet instead of measuring our specific bar magnet. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? It shows that the forces are variable at the top and bottom of the tube and that they need time to be evened out. Here's the evaluation. So the assumptions that we used were that we assumed that there was negligible air resistance on the bar magnet flowing through the tube. We also assumed that the bar magnet was dropped at the same way each time. So the error is that the bar magnet was dropped differently in terms of angle, spin, and initial speed each time. The effect on the results was that the experimental speed measurements varied each time, not due to chance, but due to error. So we might need to try to standardize a way to consistently drop the bar magnet. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Since conductivity is the inverse of resistance, reducing the conductivity increases the resistance. If the conductivity is close to 0, then this will cause it close to be infinity. This will create a large electric field, which will cause the magnet to fall incredibly slowly or even not move through the tube. Thus, if we reduce the resistivity to 0, then it would fall incredibly fast. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The holes would cause breaks in the current, which would reduce the upward force the aluminum exerts on the bar magnet, which would make the bar magnet fall faster. Thank you.